Hi class, welcome to Refrigeration and Air Conditioning, lecture number 7, Thermodynamic Principles of Refrigeration using CoolProp, Part 2. Alright, so in this lecture we look at thermodynamic property diagrams. These are some of the most essential tools for understanding the behavior of the fluids and also understanding your particular process from a thermodynamic sense. Okay, so it gives us graphical representation of the process paths, how your process is proceeding um, by monitoring properties like pressure, temperature, specific volume, enthalpy, entropy, etc. And these diagrams could be used for not just to get better insights about your particular system or process, but also to help with improvements. Okay, so it helps you identify and solve problems and make improvements like improvements in energy efficiency, etc. So these diagrams help you to understand the phase of the working fluid in your process, and they are particularly useful for machinery like turbines, compressors, and heat exchangers. So one of the first property diagrams that was introduced to you in this course in early lectures was the phase diagram of water. Uh, in this case, the two properties that were used to create this diagram or describe this diagram are pressure and temperature. Okay, and what was on there in this diagram was the location of different phases. Okay, so it told you where the water existed as gas, as water vapor, and water existed as ice, as solid, and water existed as liquid, and also the critical point above which the water exists as supercritical fluid. Okay, so all this information was provided to you based on relationship between pressure and temperature. There are several lines here. These lines are called saturation lines, okay, because they are in equilibrium between two different phases on this line. In this case, you're at an equilibrium between the liquid phase and the gaseous phase. So this is the you could call it the saturation line for vapor-liquid equilibrium. Similarly, there is a saturation line between the solid and the liquid, sorry, vapor equilibrium and liquid and solid equilibrium. There's also a point where all these lines intersect, which is called the triple point. Okay, so essentially, this line, this phase diagram is a description of these three lines. Okay, these three lines tell you about the boundaries which separate the phases. Now let's use CoolProp uh, to look at this phase diagrams. So we'll be generating this phase diagram using CoolProp. However, as you can see in this picture, we are only creating one particular line between liquid and vapor. Liquid and vapor. That's because you know CoolProp doesn't allow you to uh, do solid phase calculations. Okay, it's only meant for vapor and liquid. So let's create this particular line, which is equivalent to this line for water, for different fluids. So we'll do it for water, R134A, R600A, R410A. So how do we do that? Open the Excel file called Property Diagrams. Go to the Water Diagrams tab. Over here, you can see that I have um, several columns here. And the first column is for varying the temperature from water's um, melting point to its boiling point. Um, so for those range of temperatures, we are calculating the pressure using this formula. And as we had described in the class several times, when you have a temperature input and a quality input, it doesn't matter uh, for the pressure output whether the quality is 0, 1, or any value between 0 and 1. In any of those situations, it is going to give you the saturation pressure, which is the same for any quality on the saturation curve. Okay, so I could calculate this even with the value of 0 here. Okay, it will not make a change in my plots. So anyway, so the first diagram is calculated by just using a basic equation for pressure based on temperature and a quality value. Okay, and the pressure output is in pascals. If you want to convert to kilopascals, you divide by 1000. Okay, do the same thing for other refrigerants. So in this case, it is um, water. In the other case, it's R134A. So you put in the R134A formula here, and the same method. I've chosen different temperature ranges for R134A because of its um, differences in its melting and boiling points. So it can start with a much colder temperature and it ends up at almost the same temperature as the highest temperature. You can further increase the temperature also if you'd like. Same thing for R600A. I've changed the temperatures from -80 to almost 134 and another refrigerant. So typically R134A is a refrigerant found in refrigerators. Same with R600A. R410A is a refrigerant found in air conditioners. Okay, so that's how you calculate the saturation curves. And you can compare the saturation pressures for the same temperature between these different fluids, if you like. All right, so that's a very easy way to calculate our first phase diagram or the first property diagram, which is between P and T. And remember, majority of the time, temperature is used on the x-axis and pressure on the y-axis for PT diagrams. Okay. The next important diagram is a PV diagram, or pressure versus specific volume. Okay, so here it looks something like this. Okay, so it has, so remember this curve, we are looking at the same curve. Okay, we are looking at the same curve where the liquid and the vapor are in equilibrium. Okay, but if we look at the same curve between pressure and specific volume, it will look something like this. Okay, it will look something like this. For the same curve, for the same conditions, pressure and temperature looks something like this. PT looks like that. PV looks something like this. Okay, this line represents the same line here. Okay, so where is the liquid and vapor here? In this case, vapor is here, liquid is on this side, right? In a PT versus diagram, in a P versus T diagram. And liquid plus vapor mixture is exactly lying on the line. Okay. However, in a P versus V diagram, vapor is on this side, liquid is on this side. Okay. And this is called the critical point. And critical point is somewhere here for this. Okay. This point represents this point. And what happens on the inside? This is where liquid plus vapor is. Okay. So this line, whatever is happening inside that line is basically this whole area here, liquid plus vapor uh, mixture. Same thing here on the line. Across the line on either side It's either vapor or liquid, and in this case, the same. On this side is liquid, on the right side is vapor. Okay, so let's try creating this pressure versus specific volume plot in CoolProp. So go to the water diagrams and okay, it's this one. So if you look here, there's a red line and there's a blue line. So the way to calculate this line is you already have the range of temperatures and pressures in here. Now what you do is you already have the pressure that you need for your y-axis. Okay, now you need two ranges of specific volumes, one for liquid and one for vapor. Okay, and how you do that is by making sure you're choosing the phases correctly. So for vapor, the equation is of course you calculate density first and you do 1 over density. So specific volume is 1 over density. You can see the formula here. But how do you calculate the specific volume of vapor? So you calculate density at the correct temperature that you have here, but you use quality of 1. Okay, quality of 1 means it's vapor. So in this case, the quality matters. Okay, temperature and quality, if you change this to quality of 0.5 or something, you'll get a different number. Okay, it shouldn't be 0.5, it should be 1 here because you're looking for vapor. Okay, and for liquid you choose a quality of 0. So temperature and quality, and the quality matters in this case. It's not like pressure. Okay, the specific volume is different for liquid, different for gases, and different for the mixture. So you create this red line by only calculating the specific volume of vapor. Then you create the blue line by only calculating the specific volume of liquid, okay, which is really low. The liquid specific volume is really low. And you probably have to use a logarithmic axis because the range of volumes are so far away, okay, because vapor have such a high volume compared to liquid, especially for water, that it's hard to plot them on the same graph on a linear scale. So you change the scale to logarithmic scale and you get that shape. Okay, so similar to this, you can create the PV charts of different liquids. Okay, sorry, different fluids. So other fluids are all plotted in here and you can see where the numbers are coming from. So use this Excel file to check out the formula and understand how these plots are created. All right, so the next one is pH diagram. For a refrigeration engineer, I would say this is one of the most important property diagrams, okay, for refrigeration, because it is easier to understand vapor compression systems on a pH diagram. There are several different types of vapor compression systems, several combinations, several stages. It's easier to understand all of them on a pH diagram because it's easy to get a sense of pressure, and enthalpy directly gives a sense of energy efficiency. Okay, and unlike this shape, most of them have a shape like this, pressure versus enthalpy. Okay, so the shape is like this. So let's create that in CoolProp. So again, going back to the same file, let's look at water. So we created two specific volumes before. The same way you can create specific enthalpy. Use the formula H, Q equal to 0 for liquid, Q equal to 1 for vapor. again, it turns out that the vapor will be on the right side and the liquid will be on the left side. Okay, and wherever they intersect is the critical point. Okay, um, so the same thing for different fluids. You can see the shape for different fluids, the shape is slightly different. Okay, you can see some of them are much sharper, some of them are like this. So if you compare all of them, you can see the shape of the dome is different for different liquids. And later on, you will see that the vapor compression cycle is typically denoted by something like this, okay, on this chart. And each of these process paths are, you know, part of some particular process in vapor compression system, okay? So this is basically compression, and then there's a condensation, then there's expansion, and then there's cooling in the evaporator. So we denote the actual cycle that happens in a refrigerator on a pH diagram. So the shape of this particular dome for different refrigerants mean that they have different energy efficiency, cooling capacity, etc. So you could compare a lot of different refrigerants and do a lot of modeling on how they would compare to each other purely from a refrigerant standpoint using their phase properties and pH diagram. All right. Okay. So what's the next one? The next one is TS diagram. So after the pH diagram, I think the next most beneficial for refrigeration engineers is the TS diagram. In fact, a lot of textbooks primarily work with TS diagram over pH diagram, but in the industry, the go-to diagram for most engineers is the pH one. In academia, it seems like TS diagram is more preferred. So here, the dome looks like this, okay, and it's between temperature on the y-axis and entropy on the x-axis. We haven't studied much about entropy. We have learned exactly what enthalpy is in the previous lecture and how it relates to internal energy and pressure energy. Um, it's a little bit of a mystery what entropy is for you, at least in this course, but we'll try to learn that in the next lecture. But for now, just assume that entropy is also a property that is dependent on other independent properties. It's a calculated property, and it's important, especially when dealing with isentropic processes or isentropic efficiency. Also, in general, to understand the efficiency of a system. Okay, so let's try to create these plots. Um, Again, if you go back to the Excel file, property diagrams, this is where you're calculating entropy. And by the way, all the properties that we are calculating today are specific. Okay, they are specific properties. They are per kilogram. So the specific entropy for liquid, the formula is output is S. The output formula is S, and it's again between temperature and quality of 0 for liquid properties, temperature, and quality of 1 for water vapor properties. Again, the vapor seems to be on the right side and the liquid is on the left side. Okay, forget the color change here. The orange is on the left side and the blue, which is the vapor line, is on the right side. And you can do that for all other refrigerants too, um, and compile them, and you can see again that there's the difference in shape for each of them. So the same thing I mentioned earlier, depending on the shape, the efficiency and the range of numbers, the efficiency and the capacity of the system for different fluids will be different. Okay. Before we learn more about the isotherms on property diagrams, I would like us to revisit quality that we learned in previous lectures. So we know quality is the mass fraction of vapor in a liquid vapor mixture. And we know that the liquid vapor mixture is here in this plot, you know, and in these plots, it's inside the dome, right? In these plots, the liquid vapor mixture is inside the dome. How does the quality of that mixture vary along left to right or along top to bottom inside the dome here? Okay. On this line, the line is so thin, it's hard to tell how it varies on the line. Okay. You cannot tell quality using the P versus T diagram. Okay. There's no area. It's just always on this line. But in these plots, we have this whole area uh, that is surrounded by the saturation lines, and inside them we have different quality mixtures. How does quality vary inside these lines? So if I picked one particular property, and if my mixture of gas and vapor, gas and liquid, is somewhere here, and that specific property is Y, okay, in this case it will be somewhere close to 5,800 or something entropy. If I know the value of that, and I know the corresponding, for the same condition, for the same temperature, the corresponding specific property at liquid line and the vapor line, basically the saturated liquid and the saturated vapor. So if I know these three values, okay, I can calculate the quality. What this tells me is, let's say if I'm exactly at the middle here, okay, if I'm exactly at the middle between these two values, then my quality will be 50%. Exactly here will be 50%. And exactly here will be 100% or 1, okay? And exactly here is 0%. And that is true for any height. So if I create a ISO lines for quality, it will look like it goes from the center all the way to here. That will be a quality of 0.5, okay? And this line is quality of 1. And then there could be another line here that's quality of zero point 0.9 or 90%, okay? So that's how uh, several of these lines would look like for quality. So anywhere in here, okay, you can calculate what is the mixture ratio or the quality if you know the exact temperature and the corresponding value of the mixture, the corresponding specific property of the mixture at that location. Then you know the relative location where you are, and you can calculate as a percentage how much gas is there versus liquid. If you had paid attention to when I showed the graph here, you can see this is exactly what these lines are showing you. Okay, this is the saturated vapor line, quality of 1, and right next to it, quality of 0.9, and exactly in the middle, if you take any line left to right, this line is a quality 0.5 line is exactly in the middle. Okay, so this tells you that it's fully vapor here, okay, and it linearly varies the mixture ratio all the way to fully liquid here, which is quality 0. Okay, so remember this whenever you're looking at a phase diagram. Okay, um, remember that um, when you're looking at a phase diagram, and when you see a plot between a specific property and pressure or temperature, for example, these three ones, right? So this is any point inside. If you know the number here, you know the quality. Okay, all right. We just looked at ISO quality lines, how the quality varies between inside the dome and outside the dome. How do temperature vary for pressure versus enthalpy and pressure versus specific volume plots, right? Um, so in this particular case, we are looking at pressure versus enthalpy. This is how temperature, isotemperature lines, isothermal lines would look like on a pH diagram. So if you pick any temperature, okay, so these are all liquids, okay. So it the pressure increases tremendously with enthalpy for the same temperature in the liquid region, okay, and then it remains constant. It's constant pressure here in the um, two-phase region or the mixture region, and then it drops, okay, it drops quickly. So this is how an isothermal line will be um, in pH diagram. So if you have a pH diagram and you know where your refrigerator is operating between two temperatures, then you can look at those isothermal lines and create your thermodynamic cycle accordingly. Okay, so we'll try to calculate this using CoolProp, and this is an example of pH diagram for water with isothermals at these temperatures um, plotted using CoolProp. So let's open the property diagrams, go to the water diagrams. Now we already have this pressure versus enthalpy plot. What we don't know is what is the pressure enthalpy relationship for a constant temperature in the two-phase region, okay, and also outside. We know exactly on the saturated vapor and saturated liquid line, but not in the mixture region or in the fully gas region or in the fully liquid region. Okay, so what we have to do here is pick the temperatures that you want to plot. So here there are four temperatures chosen, okay, almost close to 0 degrees C and up to almost 200 degrees C, okay. So for all those temperatures chosen, we have created several different um, columns. So for T equal to 0.001 C, we created a variation of specific volume. So we started with a very high specific volume in meter cube per kilogram to a very low value. So using those two as an input, T and the pressure is calculated based on this T and specific volume. Okay, so T and specific volume is used as 1 over density is used in terms of specific volume, and you calculate using T and P, you calculate all the other things, for example, the enthalpy. Okay, so you calculate the state and also calculate the enthalpy. So do that for multiple temperatures and then plot all these lines, and you can see if you click on each line, it's picking up data from each individual set of temperature columns. Okay, so 400 degrees C for all of these, and you can see that you can replicate that constant pressure line inside and the sudden drop here. So I didn't use the liquid portion in here because it was giving humongous numbers and errors, but it is of no use for us to create on the liquid side because numbers are probably really high to be represented here because it almost shoots up vertically straight up, right? Uh, so this is how you do it for creating the pH diagram and isotherms on it. You could use the same method for creating the pressure versus specific volume of water and the isotherms on this plot. So you can see even on this plot, the pressure is constant inside the dome and it shoots up really high in the liquid region, liquid liquid vapor mixture. So this is the mixture region and this is the vapor region, right? So you can see that the um, pressure drops almost along the saturation curve uh, as the specific volume keeps increasing, and it shoots up really high in the liquid region um, outside the saturation curve, and it's constant here. So you could use the same method in CoolProp to create this, and we can look at that chart here. So you can see I've also calculated specific volume when I calculated the enthalpy. So you can see that for different temperature conditions, how all of them vary within the P versus V plot. Okay, so far we have created a working knowledge of thermodynamics relevant to refrigeration through our past lectures and also the earlier portion of this lecture. Um, so we'll try to understand the two main effects that create the drop in temperature of a substance. And if you remember the first lecture on the history of refrigeration, the two main effects that are most relevant for vapor compression cycles are expansion and evaporation. So it was easy to just say that these effects create a drop in temperature. Now let's try to prove that using um, theory and calculations in CoolProp. Okay, let's start with expansion. Now, what exactly is expansion in thermodynamics? Some people might say expansion always means there is a drop in pressure um, and also a drop in temperature. And some people might say there's a change in energy. However, expansion fundamentally in thermodynamics refers to a change in volume. Increasing in volume is expansion, decrease in volume is compression. Um, it is quite often accompanied by a change in pressure, temperature, and energy. Okay, but not always, especially when you consider pressure. Okay, so when you're talking about pressure, um, it can remain constant in an isobaric expansion. It will decrease in every other most common expansion methods. Okay, energy again, there is no energy added or removed during an adiabatic expansion. Um, in isothermal expansion, the temperature is kept constant. So there are several different types or ways in which expansion happens, right? And expansion is a method in which gas does work on the surroundings, and compression is the method in which you can do work on gas, right? Through boundary work. And here you can see different expansion processes. And as you go from left to right, the process is expansion, right to left is compression. Okay. Now, how does this expansion relate to cooling? So, for that, let's learn about isenthalpic expansion, which is one of the expansions mentioned here. Okay. Um, it's usually called throttling. Okay. In refrigeration, there is expansion happening in your refrigerator, in your air conditioner, all of them, whichever is using a vapor compression system, there is expansion happening, and that's happening through a throttling device. Okay, these are usually small, and the flow through them is very fast. So there is not a large enough area for any heat transfer. Hence, the process is considered adiabatic. You remember, if there is no Q going in, okay, so the only way the work can go in or out is, sorry, energy can go in or out of the system is through either Q or W. So when we are only talking about Q, and if that Q is zero, that means there is no heat transferred due to a delta T. heat transfer through delta T is 0. And in this case, it's not entirely true, but it is negligible or small enough to be assumed to be 0. And the reason for that is the flow is so fast compared to the heat transfer, there is not enough time for heat transfer, and the dimensions of these devices are small enough for neglecting that heat transfer. So the change happening within the fluid can be calculated uh, very close to accurately um, through this assumption. Okay, in the end, that's all that matters. If you are able to calculate the numbers to very close to what your experimental numbers are based on some assumption, then that assumption is close to being accurate. And the assumption is valid for most systems when we are talking about quick flow and small devices where there's not a heat exchanger attached to it. In such cases, the pressure drop in fluid is often accompanied by a large drop in temperature. Okay, so first of all, isenthalpic means H1 is H2, and we'll get to that equation really quick. In most textbooks, they will just define Q equals 0 and isenthalpic, but we should derive that from the second law. Sorry, from the first law of open systems. Now, this pressure drop in fluid I mentioned is most commonly accompanied by a drop in temperature, but in some cases, the drop instead of dropping, the temperature can remain constant or even increase. And it's different for different fluids, and it's based on some parameter called Joule-Thomson coefficient. Because of that, isenthalpic expansion or throttling is also named after Joule-Thomson, and it's also known as Joule-Thomson expansion. Now, what exactly is all this? First, let's look at the equation. Okay, this is the uh, first law or energy conservation for open systems. Okay, you can think of this as an open system, right? If you look at a control volume here, things are going in, things are going out. So it's an open system. And this is a throttling device, okay? So it's like a throttling valve where there is a sudden change in area, okay? So you have to go through a small area and then expand, okay? So what is happening here? If you look at Q minus W equals delta H, where you have H2 here and H1 here, okay? And you have kinetic energy plus potential energy, okay? The pressure energy is inside this. We had discussed that before. The P by rho is already part of the enthalpy. Now, we are saying that it's hard to transfer heat through this, or the amount of heat lost through the pipe or through the expansion area here, because it's flowing so fast, is less or it's negligible. So the assumption here is Q is 0. Also, there's nothing moving here in the boundary. So you could say that there's no work done. Okay, the two things are 0. And compared, it turns out that when we did all the measurements, compared to the change in enthalpy, these values, there is definitely a change in velocity, okay? But compared to this number, the change in kinetic energy is also negligible. There is not much change in potential energy within the small region. There is not much change in height. So that's also negligible. So what this tells you is delta H is 0. Okay, that's what they're saying. So it's an isenthalpic expansion. Okay, there's no work done, and in this case, it's isenthalpic. Okay, adiabatic does not mean isenthalpic. Is not necessarily isenthalpic. Okay, that's the confusion that most people will have if I just defined it based on here. If you just say it's adiabatic and just because of that it won't be isenthalpic, okay? It becomes isenthalpic because we do a lot of other assumption. We assume that there's no work. We assume that there's no big kinetic energy change that we have to consider. We assume that there's not a lot of potential energy change. And if all three of them are zero, then an adiabatic process becomes isenthalpic. Okay, so all of those assumptions are made whenever you have a throttling valve in refrigeration. Now, how do you um, uh, okay, before we go into that, these are the typical types of throttling valves devices used in refrigeration and air conditioning. Okay, there's the adjustable valve where you can change the area. There's the orifice plate, which is a plate with a small orifice. There are tubes with small diameter, long tubes that look like this. This is the most common in refrigeration, and these kind of valves are most common in air conditioning. Okay, and some special applications use a porous plug too. So these are the typical throttling devices. Though there's a big pressure change before and after. Okay, and if you actually look at the specific volume of the fluid, there's a big change in the specific volume too. So actually the expansion is defined based on that change in specific volume. All right. So how do we know whether if it goes through a throttling device, whether it will start cooling or will have no effect or it will start heating up? For that, Joule-Thomson coefficient measures a parameter defined by this equation. It's a change in temperature or change in pressure at constant enthalpy. Because it's an isenthalpic process, right? We try to find the relationship between temperature and pressure for the fluid um, under consideration. So what we do is we create these uh, temperature versus pressure. Um, we create isenthalpic curves in temperature versus pressure plot. Okay, this is not a plot that I had discussed in this lecture so far. Um, Engineers usually don't use this plot. They have other ways to determining this Joule-Thomson coefficient. But imagine a plot where you have any particular fluid, okay, and you have temperature on the y-axis, pressure on the x-axis, and you have constant enthalpy lines. They would look like this, okay. Enthalpy is constant, okay. So typically they increase here, the temperature, and then it reaches a constant value and then it drops, okay. So that's how you could plot this for different fluids in CoolProp if you would like. Um, I haven't done that for this lecture, but it's easy to create this, okay. So it's easy to create an H equal to constant line on T versus P for any fluid. Now, the question here is where on this chart you are for you to observe a cooling effect. Now, let's say you are dropping in pressure from here to here, okay? So you dropped in pressure from here to here. The temperature actually will increase. If you dropped in pressure from here to here, okay, your temperature actually will decrease. So depending on where you are on the enthalpy curve, isenthalpic curve, okay, what is your initial condition and how much pressure you're dropping, uh, it will depend on that whether you will do any cooling or not. Okay, so if you're if you draw a line, okay, at a location where the there is no more increasing and there's an inversion point, that curve is called inversion curve. Okay, so if you're on the left side of the inversion curve, you will always cool. If you're on the right side of the inversion curve, um, you'll always be heating. If you're exactly on the line, nothing will happen. Okay, So if you're very close to the line, you could probably end up having the same temperature. So basically, we are looking at the slope of that line. That's what this Joule-Thomson coefficient is. So most gases are, if you plot it, most gases, this region is more prominent, and under most standard conditions, they will cool. Okay, and this is typically happens with the refrigerants, and this is true for some gases, not many. And no heating or cooling, it is even more rare for this to happen. This can happen for some real gases, but for no heating at all, or cooling at all, that happens even more rarely. Um, for ideal gases, H is a function of T only. Okay, um, s- but such ideal gases don't exist. Most gases are real. There is a small dependence on temperature. Okay, so that's why the expansion creates this um, cooling effect. So if the gas is more real, then the bigger the cooling effect. Okay. All right. So now let's use CoolProp to further understand the isenthalpic expansion and see the cooling effect on most gases, um, and by how much. We'll also learn how to plot the isenthalpic lines for checking the inversion of temperatures and pressures. All right, so open the CoolProp throttling Excel file. Um, we'll start with air. What we have here is I'm giving the initial condition, which is on the right here, and it's a plot between temperature and pressure. And this line is basically isenthalpic line. The enthalpy is constant. And the constant enthalpy value chosen here, in this case, is the enthalpy at the beginning. So whatever initial enthalpy you give, right? So if you change this to 34, whatever that initial enthalpy is, right? From there, you're drawing a constant enthalpy line. So you change the initial point. If you move the initial point up or down, you'll get different enthalpy, constant enthalpy line. So and the name of the line is written here, right? Name of the enthalpy. So let's go back to, let's say, 36. Okay, so this is the enthalpy, 413.61 across this line everywhere. What you straight away notice is this is a really high pressure, 120 bar, and you're choosing a high temperature, 36 degree. Okay, let's say the room temperature is 36 degree. So you will have to expand from 120 bars to almost down to 5 bars, okay, almost 115 bars of expansion, a drop in pressure, to get a lower temperature of 15 degrees, roughly 15 degrees. So when you are expanding here, okay, and you can calculate the volume changes too. I haven't included the specific volume change. You can check the specific volume here and just specific volume here, and you will see that the specific volume is much higher here because you expanded, right? Pressure dropped, temperature dropped, and you expanded, and the specific volume will be much lower here. Anyway, um, one thing to note here is there is no inversion even in this huge range of pressures for air. Okay, so for air, you're mostly in this region. So under most conditions for air, you will cool when you expand or when you drop in pressure. Okay, when you drop in pressure using a throttling device, um, you will see the drop in temperature. And you would have noticed this if you're using an air compressor to fill your car's tire or some high pressure air compressors. Sometimes you would have noticed the air being a little bit cold, okay? And it's due to this, and it's not a lot noticeable. Now, what about nitrogen? Almost the same. Okay, so you start from, let's say, 30 degrees C. Let's put everything 30 here. So 30 for air, it was coming down to almost, um, I want to say 5.23, sorry, 8.23 degrees. Um, for nitrogen, it's cooling down to almost 10. Air was better. Oxygen is a lot better. From 3120, it cools down to almost 1.94. Okay, but the starting pressure is really high. For helium, you see, now we see the inversion curve. Okay, so if you are in this part of helium, you will be heating up. If you're in this part of helium, you'll be cooling. Okay, so helium is kind of different. Hydrogen, again, also mostly heating up. So if you're using helium and hydrogen, uh, you'll be mostly ending up heating using expansion. Now let's look at real refrigerants, okay? R134A, okay? And you don't really need really high pressures. You're using low pressures for them to be in vapor. Um, so you can see that it's the drop from 7 bar to very small change in pressure gave you a big drop in temperature. Okay, there's a big drop in temperature. 7 bar to 1 bar, you went from 30 to 15. Um, what if I change this to 3 bar? So even a 3 bar drop from 30, it's dropping to almost 24. Okay, R600A vapor, the drop is also significant. Okay, now one thing to note here is in a real refrigerant throttling device, okay, it's not gas that's coming here. Okay, if you're using something like R134A, it's basically um, liquid coming here. Okay, it's only for air cycle refrigeration that there's no liquid or two-phase. For air cycle refrigeration, the throttling device has air going through it and it's vapor on both sides. And you saw that air doesn't provide a lot of cooling. I mean, it needs a lot of pressure drop. Okay, if this was just 7 bar, okay, the drop in temperature is not much. Okay, it's going from 30 to 28.6. Compare that to R134A, 7 bar, it goes from 30 to almost low 15. Okay, so these refrigerants do a better drop even if they are going in as vapor, but they actually go in as liquid. So what happens if they are going in as liquid? So if you consider the phase of the fluid that's going through the expansion device to be liquid, um, what you can see here is the dramatic drop in temperature for a small range of pressure. So if you're considering R134 as a liquid, which it is, um, and you can confirm that using the phase um, SI function. So if you chose the initial condition 3010, okay, um, you're mostly in liquid state. And if that is the inlet and you do a constant enthalpy line, you'll see that the constant enthalpy line quickly drops in temperature as you drop in pressure. So if there is a constant enthalpy expansion and the fluid that's going in liquid state, then what will happen is a sudden drop in temperature. You can see that if you look at the orange line here. So this is basically telling you the quality. Of course, -1 doesn't mean anything. The -1 basically means it's fully liquid. Okay, fully liquid. Okay, that's what RefProp does for single phase. So as soon as it starts becoming a mixture, okay, from here on it's a mixture. of liquid and vapor, and the quality goes from 0 to a higher value. So that means it's evaporating. So when a liquid enters a expansion device, the drop in pressure quickly causes more liquid to evaporate, and now the drop in temperature is more dramatic. What actually happens in real refrigerants is that it's actually a mixture that goes in, okay, somewhere here, and then it drops further, just like a liquid going in. So if you started here too, it will drop significantly. Um, so that's not exactly Joule-Thomson expansion of gases. That's more like expansion happening in a expansion device. All I'm trying to tell you is the drop in temperature happens in the expansion device. That's where all the temperature drop happens, and it is a combination of the Joule-Thomson effect, which you saw here, um, where just the expansion drops the temperature of gas. Plus, it also includes um, phase change, which is why the drop in temperature is more significant when you have a two-phase fluid or a single-phase liquid going into the expansion device. Okay, and all the equations that are used to calculate this isenthalpic line and the orange line are all available here. So play with it to further improve your understanding of this. Okay, so that's about expansion primarily as a cooling process, even though I touched upon a little bit about evaporation. But now let's focus more on evaporative cooling. Okay, so in the other case, it was a change of volume, even when there is no two phases, even when there was only single phase, the change in volume affected the pressure and temperature. In this case, we are primarily looking at heat absorbed to change phase or latent heat of vaporization. Okay, um, there's many ways of teaching this. What we look into in particular is we'll try to understand wet bulb temperature again, and we'll do an experiment in the class where we will use different fluids and look at which fluid creates a bigger drop in temperature. And then we'll look into their properties and try to figure out which particular property. And um, in this case, it's basically the wet bulb temperature that creates the bigger drop in temperature. Okay, so wet bulb temperature is an important concept in evaporative cooling. This is the lowest temperature that can be achieved through evaporative cooling. Can be used for comparing different fluids, even though primarily this is defined for water. I will show you how to calculate it for other fluids so you can estimate a comparison between different fluids which will drop the temperature more. You have done this calculation of energy balance before, okay? So at steady state, okay, if you have a wet bulb thermometer and you're measuring the properties or measuring the wet bulb temperature using a wet bulb thermometer, it's essential that you consider steady state, okay? So at steady state, this is the energy balance. The sensible temperature change of air, okay? Temperature change of air from wet bulb temperature to dry bulb is equivalent to the energy absorbed during evaporation of water. Okay, so energy from here is going to evaporate the water. That is where we created this equation and then we iteratively solve for T wet bulb, right? So this is what we did in the previous lectures, okay, where W is the humidity ratio. W saturation is humidity ratio at saturation. Saturation means humidity is 100%. Okay. So how do you do this for other fluids? First thing is, I would like you to further understand uh, how that energy balance is coming. So when you're using a thermometer and you have liquid film, like a wet wick around it, um, and you're slinging the thermometer in the air, you can just focus on the reference frame of the thermometer and assume that the air is moving around. Okay, so you'll have a boundary layer like this. Okay, a film of water and a film of air and moisture, and then air is moving across all those films. So in this case, if you take a cross section here, so there's a water film at a low temperature, and we're talking about steady state. Okay, steady state. So there's a water film at low temperature, and that temperature is wet bulb temperature. Okay, and then right above that, there's a layer of 100% humidity, because at steady state, the lowest temperature possible here is only possible because it has evaporated and reached the maximum evaporation rate, and that maximum evaporation rate will create a 100% humidity layer of moisture right above the water. Okay, so the evaporation is at steady state, and now there is air that is moving around due to the slinging of um, the uh, wet bulb, and that air is constantly losing temperature and pulling more moisture out. Okay, and that air is going from a temperature of dry bulb temperature to the wet bulb temperature. So the amount of heat that is pulled from this air to reduce its temperature to the wet bulb temperature and then bring some moisture out is enough to vaporize more water and bring some moisture in here. So continuously this is happening to maintain 100% humidity here and to keep evaporating the water. And eventually water will fully evaporate, and after it fully evaporates, the temperature TWB will be equal to TDB. Okay, so this is what's happening when you do a wet bulb thermometer measurement. Um, and if you replace this with other fluids, okay, for example, if you replaced water with alcohol, what would happen to the temperature here, right? Typically, alcohol is so volatile that you don't even have to sling it. It will evaporate right away in air. So you'll basically use the energy balance that we just talked about. The heat required for evaporation is the heat removed from air. Okay, so then you will do the sensible heat change, which is we'll assume that the sensible heat change is enthalpy of the air initial versus enthalpy of the air final. Initial at dry bulb temperature and final at wet bulb. And same thing for latent heat. There is a vapor phase at wet bulb temperature and liquid phase at wet bulb temperature. You check the enthalpy of vapor and liquid, find that difference to get these latent heat, and you equate them. Okay, and use this equation to equate the latent heat to the sensible heat, and then you have to solve iteratively to determine the wet bulb temperature. So use the Excel file uh, for evaporative cooling. Okay, so I have created a comparison of different fluids and different dry bulb temperatures. Initially it's 25. Okay, um, and then they all have their own saturation pressure. Okay, and you do the energy balance, you get the final wet bulb temperature comparisons for different fluids here. So you can see some refrigerants create a big drop in um, temperature due to their evaporation compared to water, which is From 25, it will drop to 8.27, but there are some other refrigerants that drop much significantly. So wet bulb temperature is accounting for all the factors that are needed to account for the drop in temperature. So those factors include saturation pressure. Higher the saturation pressure, the faster the evaporation, right? It wants to evaporate faster. So the pressure is high at the boundary and it wants to get out of the fluid faster. So compared to water, all of these ones have really high evaporation pressure, saturation pressure. Then the other factor is, the enthalpy. Enthalpy in the liquid phase and how much it changes, how much energy is needed to vaporize, right? Um, then the molecular weight and things like that. So here, all of them are taken into account, and we can easily understand which one will create a bigger cooling effect while comparing their wet bulb temperature. Now, this doesn't really happen in real life where we can use all these refrigerants directly by evaporating to atmosphere because they're harmful, but I'm doing this for you to get a comparison of how much cooling is possible from one refrigerant versus the other, right? It's especially true if these things are commonly used, water, ethanol, and acetone, and you can easily feel their cooling effect on your hands when you use them, even though a lot of exposure to them is harmful, but it's commonly used in medical applications and cleaning applications. Okay, and how we did this calculation is by iteratively solving this. So I had an objective function here, and I'm minimizing this to 0 using the solver. Okay, if you go to solver, you're basically changing the objective cell, you know, like objective function one by one, um, and then making this to be 0, where this is basically equating the energy on either side. Energy on the liquid side versus the energy on the substance side versus the energy on the air side. Okay, all right. So that concludes um, the discussion on the two cooling effects, expansion and evaporation. Um, and we'll learn more in the next coming lectures. Thank you.